Welcome back to Spacebusters, the channel that makes you think for yourselves. Firstly, let's take a look at Ripley's explanation of comets, the dirty snowballs of the cosmos. These things are apparently flying aimlessly around the sun, losing copious amounts of their mass as they get closer, only to disappear off into the void until we spot them coming back again after huge time periods. When they do reappear, they're still losing thousands of tons of mass as they get closer to the sun. The huge tails of debris that they leave behind, sometimes hundreds of thousands of miles long, doesn't seem to diminish their size. Maybe they're picking up more mass as they whiz off again into outer space's extreme cold. But what mass? Space is meant to be empty. Maybe they're picking up dark matter. Apparently outer space is crammed full of that stuff. Anyway, enough of that fairy tale. Lamestream science tells us that as the comet has no atmosphere, the solar wind is ripping off vast amounts of ice and debris, which we see as the tail. We, on the other hand, do have an atmosphere, and that's why our stuff doesn't get ripped away by the vicious solar wind. So our fragile atmosphere is the only thing protecting us from the ravages of outer space. Thank God for clouds, gas, microscopic particles, air, water droplets, small insects and butterflies for saving us from the destructive forces of the cosmos. How lucky we are. Now let's take a look at the moon. NASA tells us that this celestial body doesn't have an atmosphere. This thing is supposedly whizzing its way around us on the Earth, which in turn is whizzing around the Sun, which in turn is whizzing around the galaxy, which in turn is whizzing towards the Great Attractor, which in turn is whizzing outwards in an ever-expanding universe. All at incredible speeds that are hard to comprehend. So taking all of this into account, we have to come to the conclusion that if you are lucky enough to have an atmosphere, then you're safe, and you won't get all your stuff ripped away. Then why, my dear NASA fanboys, why doesn't the extremely fine dust that covers the moon's surface not get ripped away and form a tail just like the comets? The moon is following us on our journey through space at the same speed. It's just as close to the sun as we are. It hasn't got an atmosphere to protect it, so how come all of the dust is still there? Is it because our very own magnetosphere protects us? If that is your answer, then please explain why the gaseous planets of Jupiter and Saturn are still in one piece and don't resemble huge comets in our night sky every single night. Answers on a postcard, please, addressed to Head of Children's Entertainment, NASA, USA. Please share this little video far and wide and enjoy the amusing responses you'll get from the fanboys. Spacebusters, the channel that makes you think for yourselves. For question number 2, we are going to stick with our old friend, the moon. NASA tells us that we always see the same side or face of the moon because it is locked into synchronous rotation with the Earth. Just another one of those wonderful coincidences, like the moon and the sun having exactly the same angular size as each other so the eclipses can happen. They also tell us that the moon is covered with impact craters from gazillions of years of bombardment by all sorts of cosmic junk. As our own eyes show us, meteors, meteorites, shooting stars, and other celestial events in the night sky come from all different angles. For an impact crater to be perfectly round, the impact object has to hit perpendicular to the surface. If it doesn't, then the crater is elongated. This can be adequately demonstrated by dropping a pebble onto sand. Let it drop and it will make a circle. Throw it at an angle and it will make an elongated mark. Strangely enough, all the craters on the moon are circles. Therefore, we have to assume that all of the impacts came from a 90-degree angle, perpendicular to the surface. This is possible, however, highly improbable. But what about all the craters that are constantly facing Earth? Where the hell did those meteorites come from? Did they go around the Earth before they reached the Moon? Did they go through the Earth by some magical means? Is there some guy somewhere on Earth taking pot shots at the Moon with a big gun? I once heard someone suggest that the craters were formed by escaping gas from the Moon's core. I mean, really, NASA, how can you explain this one? For one, the chances of every meteorite hitting the Moon perfectly perpendicular is about as likely as Brexit happening or Bill Gates taking one of his own vaccines. And how did the perfectly circular impact craters always facing the Earth get there? I cannot wait to hear you wriggle out of this one. Spacebusters, the channel that makes you think for yourselves. In the last video, we touched on all the junk that is apparently hurtling around the cosmos, occasionally banging into stuff. Meteors, shooting stars, comets, asteroids, and all sorts of other mythical trash whizzing around in our solar system. The question this time is not so much what they are, but more the direction we see them heading. Firstly, let's take a look at something a bit closer to home: aeroplanes. We see these marvels of modern technology flying above our heads every single day. Even if we can't quite see the planes themselves, we can definitely see the noxious crap that they're spewing out behind them in the form of chemtrails. We see them going left, right, up and down, and making pretty patterns in the sky. When a plane is heading away from us, it gives us the impression that it's going downwards. Similarly, when the plane is heading towards us, it gives the impression that it's going upwards. This is due to perspective, a highly contentious but enlightening subject which we will elaborate on in future Fanboy questions. So, back to the space junk. Meteors, shooting stars, or whatever you want to call them, are only observed going downwards. Sure, they go left and right, but always only downwards. This statement is not quite true when observing the annual meteor showers of the Perseids, Leonids, etc. These events appear to come from distinct points in the night sky, the radiant, hence their astrological names. But we never see a random meteor emerging from underneath the horizon. If we were indeed living on a globe, then we should observe a good portion of these things emerging from the horizon in all different directions, which we don't. We only see them during the annual meteor showers when the radiant is low on the horizon, and the only reason we see this is due to perspective. As you will see from this answer to the very same question from a gentleman with a diploma in astronomy, he writes that they are, and I quote, all coming down from the perspective of the Earth as a whole, end quote. So again, my dear NASA fanboys, wherever we are on the Earth, why don't we see meteors with an upwards trajectory? Spacebusters, the channel that makes you think for yourselves. Question number 4 will predominantly focus on rotation and its effect on the way we observe the night sky throughout the year, or years. This subject could easily merge into the effect of stellar parallax, but that topic will be addressed in a future Fanboy question. First, let's remind ourselves of the amazing speeds that we are supposedly traversing the ever-expanding universe. As per usual, we will take our information from Ripley's Believe It or Not. As we all know, it's a perfectly sound and reliable source of information. We are spinning at 1040 kilometers per hour. We're spinning around the Sun at 108,000 kilometers per hour. The Sun is spinning around the galaxy at 720,000 kilometers per hour. The galaxy is spinning around the black hole at 828,000 kilometers per hour. The galaxy is heading towards the Great Attractor at 220 kilometers per second. And the universe is expanding at the rate of some ridiculous speed. Oh, and sorry, I forgot that we're also tilted on our axis. This is one hell of a roller coaster ride we're on. Excuse me while I just finish my balancing stone sculpture. Anyway, back to the question. Every 24 hours we revolve around to the same position and we can see the very same stars and constellations in the sky. Oh wait, we're also spinning around the Sun. Every year we revolve around the Sun and we can see the very same stars and the... Oh, hold on a minute. We're also spinning around the galaxy. Every few thousand years we revolve around the... Damn, I forgot the bloody black hole bit. Oh, hang on a minute. 50,000 plus 8 billion, carry the 1, times 32 to the power of 78 equals... Every God knows how long we revolve around the... Shit, I forgot we're also whizzing towards that Great Attractor thingy. Every Bob-dillion years or so, we revolve... Oh, sod it. Okay, fanboys, answer me this. Why do we see the same stars in the same positions, in the same constellations, year in, year out, for millennia, when you say that we're travelling at ever-increasing speeds in at least 6 different directions in a universe that's constantly expanding outwards into nothing? How is this remotely possible? Spacebusters, the channel that makes you think for yourselves. For question number 5, we will look into the second law of thermodynamics and the effect of the interaction between our atmosphere and space. As per usual, Ripley's is our preferred source of information. We live in a positively pressurized system, right next to a negatively pressurized system. In other words, we live in a non-vacuum and space is a vacuum. According to lamestream science, in between these two systems there is nothing. No wall, no container, no barrier, no enclosure, no nothing. Just a mythical threshold or boundary. Let's take a look at a vacuum chamber. Notice that it has to be a very solidly built containment apparatus, otherwise it wouldn't work. Now let's ramp it up. NASA's very own huge and monstrously expensive vacuum chamber that you and me, the tax-paying public, have unwittingly paid for. The walls on this thing are 6 feet thick reinforced concrete. They have to be, otherwise the whole thing would collapse in on itself when they turn it on. Time to take a look at what happens when you take all the air out of a container. Pretty violent reaction, wouldn't you say? That goods train container was made of some pretty robust material. Makes you think about the magical qualities of one of these, doesn't it?
But basically you can see that it's very light and it's very flexible and it's very reflective.
Do you want to give it a try? We'll come back to the preposterously expensive spacesuits in another fanboy question in the future. So in short, how does a vacuum exist next to a non-vacuum, when the second law of thermodynamics clearly states, and I quote, "When two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium with itself, but not necessarily with each other, are then allowed to interact, they will eventually reach a mutual thermodynamic equilibrium. Oh, and by the way, it also quotes this: "The second law is applicable to a wide variety of processes, reversible and irreversible. All natural processes are irreversible." So, according to the second law of thermodynamics, our atmosphere shouldn't be allowed to exist at all, ever. Fanboys, please explain. Spacebusters, the channel that makes you think for yourselves. For question number 6, we're going to look at the re-entry of spacecraft into the atmosphere, together with the escape velocity of Earth. When launching any rocket that is designed to leave Earth's atmosphere, a certain speed has to be reached to achieve an escape from Earth's gravitational pull. This is called escape velocity. The escape velocity of Earth is 11.2 kilometers per second, a speed of roughly 25,000 miles an hour, or Mach 33. And this speed has to be obtained to be able to enter space without being pulled back down to Earth because of gravity. Coming back into Earth's atmosphere, the process is called re-entry. This is supposedly the rapid braking of the spacecraft caused by it hitting the Earth's thicker atmosphere, which decreases the velocity drastically from the orbital speed of 9.4 kilometers per second in low Earth orbit. Or to put it another way, many times faster than a speeding bullet. So after the launch, our rocket pops into orbit with its brand new shiny paint job and all its fancy bumper stickers intact. It's now ready for its debut on the world's media platforms in all its glory. On the other hand, when the spacecraft encounters the Earth's atmosphere on the way down, it heats up so much that the NASA engineers have to cover it up with special heat-resistant ceramic tiles so the thing won't melt on re-entry, due to the extremely high temperatures of the carpet burn. Sorry, did I say carpet burn? I meant to say plasma burn. So how come it's travelling at the same speed, through the same atmosphere, at the same angle, and in the same direction of the Earth's rotation, yet no provision is made for protection on the ascent, and the spacecraft is unharmed when it reaches orbit? I'll just pop this picture on the screen while you fanboys try to work out an answer. Time's up. Remember to put your names at the top of the papers. If you have any trouble with this, just ask the teacher. Spacebusters, the channel that makes you think. Question number 7 involves a very simple experiment that anyone can do with a pair of binoculars in their back garden on a starry night. Find a bright star in the night sky, preferably one that is on its own with no stars around it. Now take your binoculars and look at the same star again. You will notice that you can now see more smaller stars around it. Now, the immediate fanboy reaction to this will be that the light is not strong enough to be seen by the naked eye. But wait. If you go out to the countryside, where the light pollution is not so bad, these small points of light are clearly visible without the aid of binoculars. So we know that the light is definitely strong enough to be reaching our eyes. Again, referring to Ripley's, light can travel forever and ever through the void of space. But apparently when you're in your back garden, it stops a few hundred feet from where you're standing. I know, light pollution and all of that, but if you now take an even more powerful telescope, even more points of light appear in your field of view, and that will keep happening by increasing the optical power of the telescope. From these simple observations, we have to conclude one of two things. Number 1, these points of light are too weak for our eyes to see them. Number 2, these points of light are too far away for us to see them. As we have been told by our learned scientists, light waves can travel millions of light years through space, and it can take millions of light years for them to reach us. So the light from some of these distant stars is supposedly millions of years old by the time it reaches us. If the light from these distant stars did truly travel bobdillions of miles through space, then why did it stop a few hundred miles from Earth? This does not make sense. Surely, no matter how small the point of light is, it should still reach our eyes, eventually. Yes? Apparently not. Even though some of these points of light are supposedly mega huge galaxies and massive stars giving off humongous amounts of light, the light stops short of reaching us here on Earth. We need optical help to see it. The light from these distant stars has been travelling gazillions of miles for billions of years through space, dodging galaxies, gas clouds, clusters of stars, black holes, and probably a few aliens on their way to work as well, only to come to an abrupt halt a few hundred feet away. Using mainstream science's description of light, when we go out at night, we should be bombarded with a night sky completely lit up by the trillions of stars that are apparently out there, all hitting us with their light no matter how small an amount it is. The fact is, and this is easily proved, that light does not travel forever and a day. If it did, then we could light up a large room with a hand torch, because the light waves would constantly rebound off the walls in all different directions, eventually lighting the whole room up. This, as we all know, does not happen. Ah, but in space it's different, I hear you say. Space is empty, it's a void, it's a vacuum. There's nothing in it to stop the light waves. Apart from shed loads of dark matter and dark energy and dark chocolate, not to mention a few billion galaxies that this light conveniently bends around. Similarly, when our astronauts go into space where the view is not obstructed by the Earth's atmosphere, they should be constantly and completely dazzled by an awesome array of starlight coming at them from everywhere and all directions. Or all of the starlight is blocked out by a flaming ball of burning gas, our sun being constantly visible in the sky. Whatever option you choose, your wet dream heroes can't seem to make their minds up about it either.
Yeah,
all
because
the
you can
time.
see,
It's-
you can see the stars.
Oh, yeah.
You know, and pretty much all the time.
I don't recall during the period of time that we were photographing the solar corolla what stars we could see.
I don't remember seeing any.
You can't have it both ways, fanboys. Either light travels forever, or it doesn't. Period. Spacebusters, the channel that makes you think, oh, whatever. The next question was going to be about the moon's orbital path and its supposed effect on Earth's oceans, but we are experiencing some technical difficulties. We overloaded the free video editing software. Our excuse is as follows.
We'd revisit the moon in a nanosecond, but unfortunately we've lost the files and it's a painful process to build them back up again.
The next few fanboy questions will be very short but pertinent ones about the moon landings until we get our technical problems fixed. Please bear with us and enjoy the typical nonsensical and ultra-complicated fanboy reactions in the comment section. This one is an oldie, but still one of the best evidences that we never went anywhere near the moon, let alone land on it. Many people have covered this one in much more detail, but it's still worth another quick look. Here we see the lunar lander sitting in place on the moon's surface. Here's some footage of what happens when you fire up a rocket engine close to the ground. Dust everywhere, and this is Earth dust, not even the ultra-fine moon dust that supposedly covers the surface. So where is the blast crater? Where is all the dust that was kicked up by the descent? That thing should be filthy. Did they fill in the blast crater and then do a bit of housekeeping for the sake of the gullible audience back on Earth? Or did the magical lunar wind blow it all away? Or my personal choice, it was all filmed here on good old terra firma. How do you explain such glaring inconsistencies, fanboys?
Good afternoon, and welcome back to the Fanboy question series. This question will address a concern I have over the validity of the premise that the moon is the reason we experience tides. The moon supposedly exerting a gravitational pull on the Earth's oceans is a postulation that is so full of holes that it's worthy of its own Fanboy series, but that's not what we will be looking at today. Here's our usual source of information explaining the tides as we were all taught in our indoctrination camps. You remember school, don't you? That place where we learned about Pavlov's dogs in class. Then the bell rang and we all had lunch. As you can see by the diagram, the moon pulls the oceans up as much as 1.2 meters when it's overhead. I find it puzzling that this same gravitational pull doesn't seem to affect smaller bodies of water the same way. The force is a constant. It's exerting the same force on an ocean or a pond. Even your lauded hero, Sir Isaac Newton, once confessed, the moon's gravitational pull on the Earth's oceans is the least satisfactory part of my theory of gravitation. As an example, you're sitting on your boat in the middle of the ocean drinking a cup of coffee. The moon is directly overhead and it's pulling the mighty ocean up 1.2 meters under your boat. But your coffee stays perfectly stationary in your cup. An unknown force is lifting trillions of tons of water in the ocean, but leaving a few grams of coffee completely untouched. Our bodies are 55% water. Shouldn't the moon have an influence on us as well?
Everybody out of the swimming pool, because the moon's coming over.
The purpose of this question is not to argue the validity of the gravitational claim. It is simply to ask, where else in nature does this form of selective force exist? If we take magnetism as an example, a magnet will attract a smaller piece of metal easier than it will a large piece. In our physical, observable world, a constant force will affect a larger mass object less than it will a smaller mass object. A magnet will easily pick up a paperclip, but that same magnet cannot pick up a car. If we extrapolate this easily provable natural phenomena to the moon's alleged gravitational pull on the oceans, then surely the same force should also affect every body of water, however small, in the same way. If your argument is based on a greater surface area having an exaggerated gravitational pull, then how do you explain the well-documented facts that smaller bodies of water can have extremely high tidal displacement, but can also have no tides at all? The Caribbean is a perfect example of a non-tidal group of islands. Sitting between three large bodies of tidal water, the Caribbean islands do not experience tides. The Bay of Fundy has a huge tidal range of about 4 meters, sometimes reaching 16 meters. But Lake Ontario, which is comparable in size and only 500 miles away, has a tidal range of less than 5 centimeters. This is analogous to a magnet picking up a shipping container and leaving a paperclip next to it untouched. Back to the simple question. Is there another force of attraction in nature that exhibits the same highly selective characteristics as the moon's alleged gravitational pull? If so, what is it? Fanboys, please enlighten me. Now on BBC One, the next episode of Fanboy Questions.
Captain's Log, Stardate 2019. These are the voyages of the ISS. What the f...
This question is going to be short and sweet. Here we have the spinning ball, and here we have the moon. These two celestial bodies are allegedly 384,400 kilometers apart. The moon allegedly exerts its gravitational pull on the Earth's oceans, and the Earth, being 4 times larger than the moon, exerts its gravity on the moon. The ISS is supposedly flying at an altitude of 408 kilometers above the Earth. If the moon's gravitational pull is strong enough to pull the oceans up, and it also pulls the Earth's landmass up a few centimeters as well, then how come our illustrious astronauts are gravity-free when they're meant to be flying in between the two celestial bodies? Surely gravity should have an effect on the ISS and the astronauts, from the moon and from the Earth. Are they maybe in a magic Goldilocks zone of anti-gravity? Maybe they're in a special orbit where the Earth's gravity cancels out the moon's gravity.
Shit, who's driving this thing? Keep your eyes on the goddamn orbit, man, for Christ's sake.
Or maybe they encountered the rare phenomena called pockets of gravity. Or maybe the whole ridiculous puppet show is filmed in a studio.
All you're watching is a puppet show, yeah, the whole world's a stage. Astronauts, they're actors, of course, and yeah, they all get paid. Look at me, Ma, I'm floating in space. No, you're not, you're lying to the whole human race.
Anyway, back to the question. Why doesn't the Earth or the moon have any gravitational effect on the ISS and the bunch of bad actors inside it when gravity is casually lifting up the oceans while they fly in between the two? How are you going to spin this one, fanboys? Pardon the pun. Welcome back to Spacebusters, the channel that makes you think for yourselves. Here we go with another simple question which will be answered by our subscribers like this, and the fanboys like this. This question doesn't involve a lot of explanation or background, so just take a look at these clips. As you can clearly see, NASA is using green and blue screen technology to make us believe that these liars or actonauts are actually flying around the Earth in a tin can. By the way, these are just a few examples. There are literally hundreds more to be found. Losing a digital signal or packet loss, jitters, latency, etc. looks like this and usually affects the whole screen, i.e. the whole transmission. As you can see from the clips, with chroma key technology, it's only the actors and props that are affected. The background green screen always stays sharp. The evidence is so overwhelming and the proof is so obvious, even to a child. So my question to NASA and the fanboys is, if you truly are in Earth's orbit, why are you deliberately faking the footage from the ISS with chroma key technology? Now on BBC One, Space Hair and Gravy Tea.
Space, hair and gravy tea. Indeed. Space, hair and gravy tea. Really? Hairspray is all we need. Seriously? To make fanboys believe. Hairspray, an enchanting thing. Allegedly, the moon's gravity can lift the ocean tides nearly 2 meters up from 280,000 miles away. But stand 5 feet away from the surface of the 4 times larger Earth with a little spray of polyvinyl pyrrolidone vegetable gum in your hair, and it wondrously stops this indomitable force from dragging your hair straight down, as our lovely model is demonstrating. The proponents of density and buoyancy would point out that hair is denser than its surrounding medium of air, and therefore falls until it meets a force strong enough to counteract that fall, like the hair roots firmly attached to your scalp, or by putting a medium much denser than the hair below it to stop its descent towards a medium of equilibrium. For example, hair below it coated in much denser vegetable gum. Or gravy tea, whichever makes more sense to you. Now let's go to that magical place called space.
NASA needs you to believe.
Fanboy proponents of gravity assert that gravy tea is a force, and therefore the reason astronauts and all of their equipment always floats around is because there is obviously no gravity in space. Which is also why everything is always secured to the walls in the ISS. This seems logical and reasonable. In gravity, this is what happens when you drop the mic. In zero gravity, the mic will stay still unless the astronaut exerts force upon it to push it in the direction he wants it to go. It will keep travelling in that direction until a counterforce impedes its movement, like a wall or another astronaut's hand. Astronaut hair is the only substance in the universe that defies these fixed and indisputable laws of physics. Without fail, whichever direction you send astronaut hair flying, it immediately snaps straight back and falls straight down. Even with short hair, once again, zero gravity, gravity. Some space hair even defies the laws of inertia and gravy tea. Watch how this hair is always fixed in one position. There is only one explanation, and that is, it has purposely been styled that way.
This is glue, strong stuff.
When in fact, here's how hair should behave in zero G. The freely moving necklace proves her hair has been fixed in place. So why spend hours purposely spraying your hair with gum instead of tying it down? There is only one reason: to make monkeys believe in this nonsense. If you still believe in this bullshit, you deserve to lose every tax dollar these lying fraudsters extort from you.
Space, air, and gravy tea. Indeed. Space, air, and gravy tea. Really? Hairspray is all we need. Seriously? To make fanboys believe.
Welcome back to another edition of the NASA Fanboy Question Series. Today we're going to look at why NASA's scientists don't seem to agree with some parts of Einstein's theories. He postulated that if one is moving at a constant speed, let's say in a car, then you wouldn't be able to detect any motion unless the car speeds up, slows down, or changes direction. So if you're traveling at say 50 miles an hour and then slow down to 45, you and your passengers would easily feel the difference. The same goes if the driver deviated slightly from his course. You would feel the effect, commonly quantified as G-force. NASA tells us that the Earth is rotating around the Sun at 66,600 miles an hour. That's motoring. If we could slow the Earth down by 5%, like the car, to 63,270 miles an hour, then I'm pretty sure we'd feel it. Not only would we feel it, but everything on the Earth would be instantly vaporized due to the massive G-force. So Earth is traveling at a constant speed, right? If it wasn't, then we simply couldn't live on it. But wait, they tell us Earth's orbit around the Sun is an ellipse. If an object has an elliptical orbit, then it has to speed up and slow down twice before it returns to its original position. To save all the nitpicking fanboys the time and trouble of pointing out that the eccentricity of the elliptical orbit with its aphelion at 147 million kilometers and its perihelion at 152 million kilometers is totally irrelevant to this argument. But I'm pretty sure some dipshit will try and use it as an argument in the comments section. The common thinking on this seemingly problematic observation is that the speeding up and slowing down of the Earth is so small throughout the year that we don't even feel it. That's not what Einstein said, but hey, let's roll with this explanation. Let's find out how small that change in speed is and try to ascertain whether we could indeed feel the difference when speeding up and slowing down. Okay class, out with your abacuses. Average orbital speed, 18.5 miles per second. Speed at aphelion, 18.2 miles per second. Speed at perihelion, 18.8 miles per second. From the slowest speed to the fastest speed, there is only a difference of 0.62 miles per second. Taken over a 3-month period, that's nothing. Or is it? The fastest speed is 67,752 miles an hour. The slowest speed is 65,520 miles an hour, giving a difference of 2,232 miles an hour. So, over a time period of 3 months, we have either sped up or slowed down over 2,000 miles an hour. Now divide that into the amount of days from top speed to slowest speed, and we come up with the result that we are either accelerating or decelerating at 74.4 miles an hour every day. I'm pretty sure that Adam over at the Level Earth Observer channel would not like to be operating his 250-foot high tower crane whilst the Earth below him slows down by 70-odd miles an hour per day. By the way, head over to his channel if you want to experience some real truth bombs. That's just the speed aspect of this conundrum. We're also allegedly tilting, spinning, following the sun, rotating around the galaxy, whizzing towards the Great Attractor, and expanding outwards intact with the universe. That is one hell of a lot of motion going on. Go outside, sit on the grass, and try and feel any movement.
You can't. Neither can I, and I've never met anybody that can. If you still think we're hurtling through space at breakneck speeds in 5 different directions, I don't think I can help you. Spacebusters, the channel that makes you think for yourselves. And now on BBC One, it's time for Children's Hour.
Sci-Fi Dan, Sci-Fi Dan, Sci-Fi Dan and his fanboy clan. What a bunch of misfits, scientists and nitwits. Sci-Fi Dan is a very silly man. Sci-Fi Dan, Sci-Fi Dan, Sci-Fi Dan and his fanboy clan.
Welcome to Fanboy Questions number 14. Today we'll be looking at, or rather listening to, the incredible sounds of space rockets. Sorry, wrong footage. These majestic machines not only fly very fast, they also make noise like you've never heard before. These things are loud. Here's a decibel chart to show you some examples of how noisy things can be. As you can see, potential hearing damage or loss begins at around 80 to 90 decibels, and the real pain kicks in at around 125. There is a number of reasons that no one can be close to a rocket launch. Heat, explosion risk, gases, flying debris, to name a few. But what most people don't realize is that the exclusion zone around a launch is also because the sound of these things taking off is literally deadly if you are too close. When the massive Saturn V rocket launched, it gave out 220 decibels, which is loud enough to set grass on fire and melt concrete. It would also turn your internal organs into jelly and melt your bones. What a way to go. The exclusion zone is usually around 3 to 4 miles. If you've ever witnessed a launch at this distance, then you will know that even at 4 miles, it's bloody loud. Now let's see how close the astronauts are to the noise. 363 feet. What? Wait, that can't be right. Yep, it's right. These astronauts are sitting in an aluminium box less than 363 feet away from a noise that should kill them instantly. Let's take a look at how these brave men and women handled this life-threatening situation. They don't seem too bothered. Looks like one guy's reading the instruction manual. Where's their ear protection? How can they talk to mission control over all that noise? Simple answer, they're not sitting on top of that rocket. They're in a studio. But I saw them into the capsule. I saw the technicians seal the hatch. Yes, you did. Let's see where they went.
Once the crew are on board, if it looks as if they're in danger, they get out and head down this tube, specially insulated against fire, and zigzagging down not to some point out and away from the rocket, but to an escape room exactly where you'd think it shouldn't be. 3.5 minutes after they get the warning in the capsule, the crew could be down here in the blast escape room via that 200-foot escape tube, 40 feet below the base of the rocket. They find themselves in a totally rubber room, walls and floors, and they head for safety through a 6-inch steel door. Once they're behind that door, it doesn't matter what comes down this tube behind them. On this side of that door, the rarely seen blast escape room itself. It's totally isolated from everything around it by a series of 24 giant springs underneath the floor and shells all round it of steel, concrete and sand.
There you have it, folks. They don't go into space because they can't.
Nobody rides in these things because they would die within seconds. Nobody died in these disasters. The only people that died in a space capsule was Gus Grissom and his crew. Gus had figured out the hoax and famously hung a lemon on the outside of the capsule. They tried to get rid of him by blowing the explosive bolts on the hatch while it was floating in the sea after touchdown. Luckily for Gus, he managed to escape before it sunk, but they finally got him by pumping pure oxygen into a training capsule and igniting it. Him and 2 others were burned alive. That shows you the lengths that they will go to protect their multi-billion-dollar scam. Okay, fanboys, how are you going to wriggle out of this one?